Today I'll discuss our paper from the USENIX security titled Meta-Sift. We've discovered that obtaining a small clean subset in order to support existing data poisoning defenses is actually really hard. So this realization leads us to the data sifting problem. How can we identify a small clean data set from a potentially corrupted data set? And let's dive into our findings and solutions. So first, let's recognize the recent achievement in machine learning and the pivotal role of data. So leading open source image models like Clip, Stable Diffusion, and Google Imagine relies on almost 6 billion image text pairs. And similarly, the recent release state-of-the-art open source large language model, Llama 2, utilizes over 2 trillion tokens. So this data-intensive nature inevitably leads to sourcing training data from various places, including anonymous online sources. However, this approach increases the vulnerability to data poisoning attacks. So in these attacks, adversarials alters training data leads to manipulated model outputs and potential security, privacy, and fairness issues. Real-world examples underscore the threat of data poisoning. Microsoft's Tay chatbot was manipulated into spreading hate speech after exposed to toxic Twitter users. Another instance is the 2013 fake Twitter attack, which causes 136 billion jobs in the United States stock market. So academically, data poisoning attacks have evolved into complexity. We've categorized them into three types of different attacks for the image classification task. One is a label-only attacks, for example, random or targeted label flipping. Feature-only attacks, for example, over Narcissus attack, which achieves state-of-the-art attack efficacy by manipulating less than 0.5 points of the data. And label feature attacks, where we're referring to standard backdoor attacks. Here we use the input-aware backdoor as a visual example. So fortunately, we also have a list of established defense against poisoning attacks. Representative categories of defenses are backdoor removal, which aims to convert a poisoned model into a good one, and poison detection, which aims to determine whether or which data actually is being poisoned. And actually, the next presentation by my friend here is also gonna be licensed into this category. And Trojan net detection, which helps to determine whether a given model is poisoned or not, and robust training. Oh, I'm sorry. Sorry, somehow it just got interrupted. All right, you guys can see it. And then it's Trojan net detection, which helps determine whether a given model is poisoned or not. And robust training, which aims to learn a good model from the bad data. All right, a closer examination reveals that this defense needs a small, clean data set, or we're referring to as the base set. For instance, our adversarial on learning technique from iClear 2020 used a clean data set to synthesize the noise. So such a small base set matters because state-of-the-art defenses requires a reference provided by the clean distributed data as the normal behaviors. But what if we do not have guaranteed access to such a clean data set? So this question leads us to the data sifting challenge or the data sifting problem. How can we extract a clean base set from a vast, potentially poisoned training set? So first, let's emphasize the importance of purity of the base set. Our initial tests show that even slight contamination in the base set severely impacts the defense mechanism. So especially we see one set of the defenses performance decreased by more than 80% with only 1% of corruption in the base set. So we ask, is there any existing methods may help? We evaluated existing outlier detection methods in order to see if they can address this data sifting problem. So surprisingly, many perform no better than random selection, failing to identify the clean samples with high precision. The reason may be that most non-outlier samples that marked with lower ranks by existing automatic detection methods do not correlate strongly to the cleanest example resized in the data set. So what about human supervision? So referring to a recent survey, it seems widely accepted that humans may serve as the final backstop for data poisoning. But is that actually true? So we tested this theory by poisoning the CIFAR-10 dataset in 16 ways and asked 48 labelers from 3 companies to identify the clean samples. With humans, well, humans actually are pretty good at spotting the label manipulations. They struggled with clean label attacks. performing only slightly better than random guessing. So one may take a closer look at the difficulty, how it is difficult to spot the poison samples on the upper right corner. So the proof of concept evaluation showed that humans are not a final backstop of data poisoning. This leads us to our proposed solution. Our idea is actually quite simple. Imagine you have a data set that contains poisons. Here we use a data set contains only data that are labeled as speed limit as an example. So we use the clean portion of the data to train a model and test on the poison portion, which surely will result in a high loss value. However, conversely, the loss will be lower if more poison data is used for training. Our objective becomes more and more clear now. How can we find a data split that maximizes the test loss over the other split? As we assume the clean samples are greater than 50% of the whole data set, the split with most samples that has a higher chance to be clean. So we formalize this whole process as a bi-level optimization, where the inner optimization trains a model on the related data set, while the outer optimization evaluates the results. So we initialize all of the weights for the inner training step as all ones, and then update them to the values between 0 to 1 following the update model, and weighting network parameters updated in the following epochs. So in total, after 2 above epochs, the samples are assigned with higher values are of higher contribution to the training process and less contribution to the other validation. Or we say they have a higher chance to be clean. So Meta-Sift workflow involves multiple sifters. Each sifter consists of feature extractor and weight network. We apply random augmentation to the data set and use sifters to assign values during test time. The final results are an average of all sifters, enabling us to identify samples that are reliably achieve high scores. All right. So we test Meta-Sift on ImageNet using the normalized corruption ratio, or NCR, metric for selecting 1,000 size base set under different poison settings. So NCR is defined as the corruption ratio by giving strategy divided by the corruption ratio produced by random guessing. And our results compared with outlier detection baselines were promising, and further results on other data sets can be found in the paper. So this impressive sifting outcomes actually stem from the fact that most of the defenses only need 1,000 clean samples. As you may see from these images, different attacks actually result in different kind of curve with respect to the clean ratio and the selection portion. So this might be an interesting future work, maybe have some impact or implication to further research. Okay, now we look at the actual downstream performance when using the base set selecting using the Meta-Sift. From different representative defenses using the selected base set, the performance using our selected base set is close to or sometimes slightly better than the base set using a random selection from the clean portion. So this observation may benefit from the process of using multiple sifters and random augmentations to identify samples that are reliably achieving high scores. Now we look at the actual downstream performance when using the base set selected using the Meta-Sift. All right. So after this, we also explore the adaptive attacks. So one straightforward method is to poison over 50% of the data set, which provides effective penetration of the Meta-Sift. However, corrupting more than half of the training data isn't feasible in real-life scenarios. We also consider 2 optimization-based adaptive attacks. One is generated examples to disguise samples so that they can achieve lower loss over the clean data trained models. And another idea is to generate noise in order to achieve higher scores on the pre-trained sifters. However, if you look at the evaluation results, we find this 2 types of attacks actually may result in a negative impact to the attack efficacy. And at the same time, by selecting only the top 1,000 examples, the Meta-Sift actually remains intact. All right, so in conclusion, we've spotlighted the overlooked issue of the base set purity amidst poisoning attacks. And after evaluating existing methods in human inspection and realizing their limitations, we introduced Meta-Sift. Our solution is open source here, and we were awarded with both availability, functionality, and reproduced batches. Exploring alternative solutions to the data sifting problem is quite crucial at the moment. While Meta-Sift offers a solid foundation, refining the clean ratio versus selection ratio can be a really interesting topic in the future. And I would also want to give a short introduction to another work from us, which will be presented tomorrow morning at session 1. I'm looking forward to seeing you guys again. Thank you, guys.